All right, variation. What is variation? The total of variation is a number that reflects how far the scatterplot points are from the line. And we should always think about that as being a vertical separation. It's not a number that we can see easily, but it grows for looser fits. So here we're looking at two unrelated scatter plots with lines of best fit drawn through them. These graphs don't represent anything in particular or our example. I just created them for this illustration. But the one on the left shows us a scatter plot with low variation as compared to the one on the right, which has higher variation. And I've represented the variation with these vertical distances. So you can see that on this graph, the pink line predicts where the point should be, and you can see that this one's actually a little bit above its predicted value. This one's a little bit below its predicted value, but they're pretty close, and that would probably make us pretty happy if we were trying to predict things. This one might be a little bit more of a concern. We're expecting the points to fall on the heights given by this line. Like in this case, if x is about 4, then we'd expect the height of the point to be about here on the line, but it's way up here. And this one is supposed to be at this height, but it's way down here. They're varying quite a lot from where we would predict them to be. That's why we call this high variation. And that might be a little bit more cause for concern if we're trying to predict the heights of these points and they're actually kind of volatile up and down all over the place. So that's what we mean by variation conceptually. Now, of course, we'll have to get into a little bit more of a quantitative discussion and put some numbers on this. As a preliminary, I want to think about what are the various reasons that our call centers have different hold times. And on our scatter plot of the call center, why are some of the points higher than others? Some of them are way up here, some of them are way down there. How come? Well, we can basically break that down into 3 reasons. 1, this variation is partly explained by their different staffing sizes, which is our x variable, our predictor variable. However, 2, there may be other unexplored factors that also help to explain the difference. And then 3, there's also an element of sheer randomness. So in your illustrations handout, I've created a pie chart that illustrates this idea. The staff size variable, x, probably accounts for some portion of that variation, but there are other factors that might also be important. And then, of course, there could also just be sheer randomness. The portion of that variation that's explained by staff size has a name that's very obvious, explained variation. And these other 2 factors together constitute what we call the unexplained variation. And you might be curious, like, how do we know how big these slices are? How do we know that this green portion that's explained by staff size should be this big instead of this big? Well, this is where we get into the quantitative analysis. So as it turns out, this proportion or percentage of explained variation has a really simple formula. It's r squared. Remember r, that correlation coefficient, the linear coefficient of correlation, is called lowercase r. And if we literally just square it, if we multiply it by itself, it gives us a decimal between 0 and 1. And that's called the coefficient of determination, by the way. But that is actually the proportion of that pie that is covered by the explained variation. Of course, the portion of the unexplained variation will be the rest of the pie. So that will just be 100% minus that other number, 1 minus r squared. So on our examples handout, the next question here is to calculate and interpret the coefficient of determination. The coefficient of determination is symbolized by r squared, and that r is the same as the the correlation, the coefficient of linear correlation that we used before. We've calculated R, by the way, for this example. It's negative 0.872. Now let's be a little bit careful when we square that, because when you square a negative number, you should be ending up with a positive number, right? So R squared is this negative 0.872. The whole thing needs to be squared so that the square of a negative number becomes a positive number. We end up with about 0.76, aka roughly 76%. And that is why, when you look at this pie chart, I drew the explained variation as about 3/4 of the pie. 24% is still unexplained. So in the near future, in this week, we're going to try to come up with other explanations and keep reducing this unexplained variation. But for now, we're just using one predictor variable. Okay, so R squared is 76%, and again, that explains the proportion of this pie, the proportion of the variation that is explained by the predictor variable that we're using. Now, it turns out that the variation itself is actually a number. I'm not too concerned about what that number means, because remember again, I said it's related to the looseness of the graph, and that's really all we need to know. StatCrunch will find the number, but the looser the graph, the bigger the variation. So we need to basically apply this 76% to that big number, whatever the variation is. And of course, this is where StatCrunch comes in handy. So if we go back to our regression display, this was StatCrunch's output when we ran the regression, simple linear regression for this illustration. And what we're looking for now is this bottom table. It says analysis of variance table for a regression model. And this, the column that we're looking for here is actually, it doesn't say variation, it says SS. I think that means sum of squares, because the variation is actually determined by adding together the squares of all those vertical distances. So we just need to know that SS means variation. But this tells us that the total variation is 239 point such and such. So that would basically represent the size of that whole pie. And if we take 76% of it, we would get this explained variation. And here again, the words are a little different. This readout doesn't say explained, it says model. So the model that we are using has explained 182 units of these sums of squares. Again, I'm not too concerned with what these numbers measure because they're a bit geometrical. They're just numbers. And then the error part is the unexplained portion of the variation. So to summarize again, this number is explained variation, unexplained variation, and total variation. By the way, when you look at this readout, it also gives you R squared up here. 0.76 is the square of this number. So if I just basically copy these two numbers, I can carry them over to my answer. The explained variation is about 182, and the unexplained variation is about 57, with that total being about 239.